Okay, guys, I think time to run. We are a bit fewer at this hour, so let's hope that the members of the teams that presented yesterday and that did some dinners and drinking in the downtown of Brno will make it soon here. So today we have the second final day of JSALT 2025. Welcome all here. Welcome also people that were not here yesterday. Like I see Loic, I see Katka somewhere. So great guys that you made it back to Brno. You know, Brno is a very magnetic place. So today we will have quite a packed agenda. We will have the presentation of two teams. TTS4ALL in the morning, Augi in the afternoon. We will have just 1 hour and quarter for the lunch, so we need to be like efficient. And I would like everyone to try to stick with the agenda, with the timing, because in the evening we have like some closing stuff and some photos, and then we need to transfer to BUT Rector's office for the final dinner. And I think that's it. Like I have nothing more to say, so I would like to ask Yannick to open the technical presentation.
Thank you, Honza. Okay, may I start? So, good morning. It's a great pleasure for me to be here to start this presentation that concludes an intensive work of 6 weeks here at Brno. So, in the name of the team, I would like to thank all the organizers, the local organizers, the Czech guys, Honza, Radim, Renata, the students. So thank you very much for this nice stay here. We could work in very nice conditions. And of course, I would like to thank Sanjeev and the DIATU team to make possible this kind of event that is really very, very important to make links between researchers all over the world, especially researchers. So we are the TTS4ALL team, so we work on text-to-speech processing, and we went from all over the world, funded by the European Commission, so it is important also to thank them, because without them we could not be here today. So why TTS is so important? Why we are interested to that? It's because TTS is a technology that could help in a very large number of situations. For instance, for accessibility, for people that have visual impairment, for instance, but also for digital inclusion, for instance, for elderly people. But also it is important for hand-free, when you in a lot of tasks in the daily, we would like to interact with a machine without using screen, without using a keyboard, because we cannot use our hands. So it could be very helpful to get this kind of technology. There is also more and more situations in which we have human-computer interaction, so it could help to use this natural language that is speech. And also it is very important for multilingual communication, for instance, for speech-to-speech translation. But the thing is that now this kind of technology is very strong, very nice performance for dominant languages like English, for instance, or Chinese, or other one. But there is a lot of part of the world population that could not use this kind of technology because they don't speak their languages. So it's one point we want to address in this project. So in this project, we mainly focus on low-resource languages, so how to collect data, how to qualify the data to make a TTS system, how to evaluate this kind of system, because when you don't have a lot of native speakers that could help you to develop this kind of system, how do you do? So this is point of research we address during this work. And also we want to explore some strategy, for instance, fine-tuning strategies to take benefit from existing TTS for large dominant languages to help to develop TTS for low-resource languages. But also we want to better understand what happened within these neural architectures we are using. For instance, and mainly we want to better understand how the speech information is contained and captured in the internal representations, and how you could use this knowledge in order to better control the TTS models. And also, in addition to this work dedicated to low-resource languages, we have worked on new applications like pseudonymization. We will explain you later what it is because I have to be brief. And we also worked on streaming TTS. So this morning, we will have 6 different parts in this presentation. The first one is about evaluation. The second one about text-to-speech for low-resource languages. The third one is about prosody control, how to control the prosody, the expressivity in TTS. The fourth one is about neural codec that we consider very important, for instance, for streaming TTS or other kind of applications. Another is about some kind of speech representation, mainly from this neural codecs, and also the last presentation will be about pseudonymization. And now, Meysam, sorry, you hidden here. I give you the floor.
Thank you, Yannick. So, on behalf of our sub-team evaluation, I will present you the next slide. So, before jumping to the presentation, I would like to ask you to imagine that you are in the dark room without any light, even without any flashlight, and you want to find the exit. The only thing that you have is a laser pointer. We know that it's not the perfect tool to find the exit, but it may help you to find the exit. So we have the same scenario, same situation in TTS evaluation. We don't have a very reliable, easy, available tool, but we have some tool that may help us to guide us toward the right direction. So usually, the TTS evaluation would be done by a perceptual test, a listening test, which we ask listener to judge the speech quality with different type of protocol like MAS, Mushra, A/B test, etc. It's the most reliable evaluation because our target user are human, but it is costly and sometimes not even feasible. On the other hand, we have an automatic or objective evaluation, which measure the quality, speech quality by a model, and we need to find a model that correlates with human evaluation as well. As our laser point, it's not the best tool, but it's available and sometimes can lead us to the right direction. Before going through the evaluation part, I would like to just give you some terminology, some definition that we have about the category of the evaluation. We have first principle or physics-based or analytical model, which are based on a mathematical equation for a given defined variable. This environmental variable should be provided to calculate this type of metric, and most of the time it's difficult to reach to this measurement. On the other hand, we have a data-driven model, which are a statistical model trained on the data. They have the capacity of generalization, so we don't need to measure every time the environmental variable, but on the other hand, they are highly dependent to the training data. In other type of the category, we have intrusive measure versus non-intrusive measure. Intrusive measure, when we need a reference signal to calculate the distance between our signal and this signal, which usually used for as a degradation measurement, and it's the most common metric in telecommunication. In non-intrusive measure, in non-intrusive metric, we call it as a reference-free metric when we don't need a reference to calculate the quality of the signal. We believe that non-intrusive metric is more suited to speech synthesis, because different output of the T-system in the same time can be valid and perfect. So the measure of distance here would be automatically adapted to the situation. Next, we would like to cover different aspects of the quality as well. So here I put some definition for different aspects of the quality that we would like to cover in our work. Intelligibility, when we would like to evaluate how accurately the speech conveys the semantic content of the given text, because we are talking about text-to-speech, not only speech synthesis. Naturalness, when we try to evaluate how closely the synthetic speech resembles natural human speech, regardless of the listener's familiarity with the language. Signal quality, where the integrity of the synthetic signal, considering factors such as noise, reverberation, and artifact is important. Speaker similarity, when we would like to target a speaker, a specific speaker, and we would like to synthesize the given speech for this target speaker. Prosody measure, which is a measurement of the expressiveness to investigate the different type of the rhythm, intonation, and emotion. So in order to work on the TTS evaluation, we come up with the Python toolkit, which is available for public, and we listed this long list of the measures that we have for different categories. Some of them are intrusive, some of them are non-intrusive, some of them are first principle, some of them are data-driven. Most of these metrics are developed by the community, and we just integrated in our work package to be easy to use, and some of them is developed by ourselves. You can see that in different categories, we have different one of them. Sometimes they are, some of them are more reliable in different contexts, and some of them are irrelevant even in some contexts. Basically, when we want to have a long list of this metric, the ideal scenario would be they should be as independent as possible. Otherwise, we are measuring a redundant metric. So here we have a Spearman correlation coefficient between these metric for a data set, a synthetic signal. And you can see that sometime, like PSQ in the signal quality, we have a high correlation with STOA from SQAIM, which shows that these two metrics, however they are measuring different aspects of the quality, they are highly correlated and maybe not as independent as we like. Here we have a barcode of our package that is easy to use, and it's open to integrate any new metric that you think is more suited. So in the next slide, I will cover the contribution that we have in the evaluation sub-team. We had two main contributions, two main experiments that we had. First, we proposed a new automatic model for evaluation of a synthetic signal. We developed a mass predictor without using a mass annotation, which will be presented by Natasha next. And then we will have an application-based evaluation of the TTS, which was developed and proposed by Aaron, and I will present on behalf of Aaron after Natasha. So before presenting our new metric for evaluation of synthetic signal, I would like to give you a context. We participated in a Blizzard challenge a couple of months ago, and this year, this challenge was targeted for a language, a low-resource language called Beeldz in Netherlands that has only 10,000 native speakers. So we knew that there is some quality predictor, but this state-of-the-art even quality predictor are not adapted to this new language, new data set, and even new speaker or TTS architecture. On the other hand, we had, with the emergence of the new TTS architecture, we had a long list of the choice to work on, to start with, to develop, to have one TTS as a final choice or final candidate for ourselves. So we needed a new measure a new metric, a new approach to help us to find the good direction. This metric may not be as perfect like our laser pointer, but it can help us to find the right direction. We come up with a quality predictor. We needed a quality predictor for synthetic signal in the new domain and new language. This need has been responded by the work of Natasha, which will present you the next slide.
Hello, everyone. So why we want to make a quality predictor? So the motivation of this work is if we manage to obtain 2 synthetic samples of different quality, we can so train a model to predict this difference. So the goal of this work is to develop a quality predictor model for synthetic speech without human intervention in training set design. And this quality predictor model could be able to predict a quality score correlated with human perception and in different language and domains. So how we can define this difference? We could define this difference during the training of a TTS system because we can collect the spectrogram emission, the loss, and the iteration number. We make the following hypothesis with this information. We can use this loss or this iteration number as a proxy for audio quality to train a quality predictor. Also, we make a second hypothesis, more linguistic, where we propose to observe if the variation in linguistic diversity in the training corpus can influence the learning of and performance of a quality predictor. So, to answer of the hypothesis number 1, during the training of a TTS system from scratch, we generated in a certain iteration a synthetic sample, and with this generation, we extract the loss and the number of the iteration. With this information, we can answer of the hypothesis number 2, where we create 3 types of database with different diversity linguistic diversity. The first one is the random database, when we have the more diversity linguistic diversity, because we have a few utterance random for each chosen iteration. The second one, we have the same iteration for each chosen iteration, so So we have a less linguistic diversity in this database. And the last one, we have the short fixed database, where we have less linguistic diversity because we have the more short sample and the same for each iteration. So an evidence for the hypothesis 1, here we can observe an improvement of 3 different metrics proving from 3 different aspects: naturalness, signal quality, and intelligibility. And we can see an improvement of most for each iteration for the random database and the fixed database, and an improvement of CER for short fixed database in particular. A second evidence for the hypothesis 1, here we have a decrease of the loss for each iteration, in particular for short fixed database. Here we have the architecture of the quality predictor. So we provide of this quality predictor model the iteration or the loss for each sample. And this quality predictor have a frozen SSL model followed by 2 fully connected layers. The loss used here is the per loss BCE. The more important here is we took 2 samples, and if the difference between these 2 samples is positive, we want the same things for their prediction. If it's not, we have a high loss. So to evaluate this quality predictor, we have 4 different data sets. The first one coming from the training of our TTS system. The second one is in the same language, but coming from Blizzard Challenge 2023. It's a recent data set. The third one is another language coming from various ears, synthetic speech coming from various ears, and the last one is the same language, so English, but more recent. All of these data have a MOS annotation, human annotation. So here we have the first result with the random database, where we can see a better result than the state-of-the-art for unsupervised approach, 0.21 for BC corpus. For us is 0.54. Also, we have a high correlation for IT corpus, BC corpus, and BVCC corpus. So the hypothesis 1 is confirmed for this case. And we have a lower correlation for SOMOS dataset than the other dataset. For the other database, we observe the same things when we have less linguistic diversity, but we can see for the worst database here, lower correlation, so the hypothesis 2 is also confirmed because the linguistic diversity influenced this performance for the iteration predictor. For the loss predictor, we also have a better result than the state-of-the-art with 0.40, for example, but we have also a high correlation for the same database and lower correlation for loss predictor than the iteration predictor. It's better to use the iteration predictor in this case. So the next steps of this work, we want to go in another system with overloss, like forward tachotron, and also with a different family of systems, because the architecture of a TTS system can influence that also. It's an hypothesis. Currently, we have a random selection for the data collection. For the future, we want a more strategic selection of this sample, depending on different characteristics like acoustic or linguistic characteristic with the distribution of the phoneme or the F0, for example. And to conclude, we have a correlation between iteration loss and human annotated MOS. The degree of linguistic diversity is important, and we have good results when we change the initial language. So the contribution of this work, we propose a quality proxy which can be used in various domains, image generation, text generation, without human intervention, and this methodology can help to obtain pseudo annotation for training data for quality predictor. So thank you.
Thank you, Natasha. So in the next part, I will cover for Aaron, and on behalf of Aaron, I will present his work on application-based evaluation of the TTS. The hypothesis is a good AI can prove itself if it can replace human tasks. In our case, a good TTS can prove itself if it can replace human speech. So we would like to use the TTS for an auxiliary task, here in this case, translation of speech-to-text translation, and generate a training data for this task. So usually in the context of the low resource, what we have usually for the translation is a pair of text from the low resource to high resource. But what we need for the speech-to-text translation, an end-to-end system of speech translation, is a low-resource speech and high-resource text. So the idea here is if we can synthesize the text in low resource with a low-resource TTS, we can generate a data set for end-to-end speech-to-text translation. And if our TTS has a higher quality, it can replace human job and provide us a speech for low-resource language. This type of approach can be applied to the two cases that we targeted. One, when we don't have a pair of speech text in the low-resource languages, or when we would like to adapt to the new domain. Imagine you have the text in some domain and you have the speech in some domain, and now you want to increase or augment the data in other domain or other context. So for that, we come up with this generation pipeline. We have a biotext data set, text from source and text for target, a pair of translation from two language. And we propose to have several TTS. Each of them are trained with different data set, and we use a F5 TTS here, which can be used as a cloning TTS, and by help of the reference or prompt signal, we can control on the speaker or prosody diversity. So our TTS, as I said, is a F5 TTS fine-tuned from English with 3 speakers. We collected the data for the Kurdish language, for 3 speakers in different scenario. One is a male speaker in a studio. One is a female speaker, which is collected data, found data, audiobook with lower quality. The third one is a male speaker in audiobook, each of them around 10 hours of the speech. And for the prompt reference, to have a control on the speaker and prosody, we use the Kurdish Common Voice with the 5000 file. For the speech-to-text translation model, we use the Whisper Large version 3, and we used biotext data, 300,000 Central Kurdish to English pair for our experiment. So we use this biotext data, we synthesize it, the Kurdish input to a speech, and use this synthetic signal to train our speech-to-text translation. Here is the first result. So our synthetic signal provide us something around 500 hours of the data, and on 2 benchmark as ASO soft and floor, we reach a blue score of 27 and 80. When we compare this result with the real speech, real recorded speech, because we had the accessibility to the real speech as well, we trained the speech-to-text translation and we reach a comparable result. By the way, we should take into account that the first line has a 0 cost in terms of human, and the second one has more than 500 human work for preparation of the data. So we wanted to investigate the impact of diversity inside the data set. So we come up with the abbreviation study when we try to remove one of the TTS or one of the data set that we had for TTS. So in the first case, we wanted to ground our speech-to-text translation performance, which we call it as a first level of the resources. We have highest possible resource. We have access to the exact test set that we have. It's an ideal scenario. We use the test set of the floor for training our speech-to-text translation. So we reach a blue score of 92, which is an ideal scenario because we are somehow cheating. We're using test set for training. But when we have only the text of this test set, we don't have the speech of this test set, and we synthesize this text with our 3 TTS system with different different data set, and using a random reference for increasing the diversity of the speaker and prosody, we can reach 79% of the accuracy of blue score, excuse me. Then, when we remove one of these one of these TTS, we can still have a reasonable blue score, but with degradation of around 5 points of blue score. And you can see that here in the third line, when we have an audiobook with a male, we have lower quality compared to the studio recording, which shows that the performance of our system, when it used the high quality speech for the training, showed a better performance. In the last analysis that we had, we wanted to know what is the importance of the reference or the factor that we imagine is controlling the porosity variation and speaker variation. So here, instead of using a random reference, we use only one unique reference to have a minimum variation coming from this reference. So you can see that the result is almost same, and there is no significant difference between these two situations. So we doubted our approach, that why we don't have this increasing of the diversity will not work for increasing the information inside our data set. So we tried to plot the speaker embedding using eKappa TDNN speaker embedding here with different system and different reference. And you can see that in this figure, the highlighted part, all systems are same with different reference, and they are separated. So we thought, okay, they should be separated because they are using the different reference. But when we investigate the reference, only reference matching signal, we see also that they are separated. So it means that neither our TTS, neither our reference are perfectly reflecting the speaker variability control that we would like, which we think we need to work more on it for the future, like adding a speaker embedding encoder to the F5 TTS model to capture the speaker information more explicitly, or find a best match reference and, input text to increase the prosodic variability. So to wrap up the first sub-team report, we had a proposition for a development of automatic evaluation of TTS without human annotation. Then we had a proposition for application-based evaluation TTS for speech-to-text translation task for low-resource language without human cost. And we had a TTS for all evaluation package, which is a Python toolkit, which is available for everybody and is open to any suggestion. And before giving the microphone to Arilas for the next presentation, I would like to use the last second to propose another metric which we can use for efficiency of the development, which we call it number of commit per number of coffee. And I know that this is not a good metric, but it's like our laser point. Maybe it will help us to find the good direction of the exit point.
So the extrinsic evaluation by saying, let's use TTS to produce speech, and if it is of really high quality, it will help a speech translation system. There are a couple of things that weren't clear to me. One is, what are you evaluating on? The evaluation is on real speech, correct? The machine translation, the blue scores, that's not on the synthetic speech.
Yeah.
Correct. So the difference you are showing is that if you take the actual human speech as the training, then you get a blue score of 31 or whatever it is you were getting. And then if you use a TTS system, you get, because it's not real speech, it's not the highest possible quality, so your blue score drops a little bit,
yeah.
Right? But to sort of persuade me that this is actually a good measure of the TTS, did you have additional experiments where you used a different TTS system which you know is worse, and then show that the translation is worse because the TTS was worse?
Yeah. Actually, the main reason that we developed the different type of the TTS here, it was that, and based on our quality measure, we found that we confirmed that the STDU TTS, the TTS that used the STDU data set, is, it was highest, it has higher quality, and shows the difference here as well. But we didn't put all the result, that I don't have it here to show you. But we confirmed this one that if we didn't consider the different architecture of the TTS yet.
Yeah.
But in terms of the data set, we observed that if your data set for training a TTS has a higher quality, you will reach a higher quality in first step of your TTS signal, then you will have a highest performance in the auxiliary task as well.
On the blue score?
Yeah, on the blue score, yeah.
Okay.
Yeah.
Yeah, I would, basically what would be nice, and even just 2 points may not be enough because you want to show a correlation between the blue score produced by different TTS systems and their human evaluations to show that a human evaluation of TTS quality correlates with blue score, which you can compute automatically.
Yeah.
So that would be nice.
Yeah.
So,
Yeah,
and then what I was also thinking was the other way to think about its usefulness. It doesn't help it's not an issue of TTS quality, it is simply the usefulness of synthetic speech. You could synthesize much more speech than 500 hours. Hopefully you have additional parallel text. Because I know that at least you said you have only 500 hours where there is speech along with the translation. Is this translation into French or English?
No, it's English.
English. So you have translation into English for only 500 hours of speech. But you hopefully have much more parallel text. And you could synthesize even more speech and see if you can get... So that would just be the usefulness of synthesis for improving machine translation. So that would be fun to know. Yeah. But mainly for your purpose, I would like to see a few more lines of different quality of TTS with human evaluation. Yeah. And see if it tracks.
I completely agree, but the point was is we didn't have time yet to evaluate perceptually with a human. Aglas will present the perceptual test that we conduct and launched already. Yeah. We are waiting for results to confirm the idea, but so far what we have as a quality of the TTS is the evaluation metric that coming from our laser point. So it's not the perfect. We know that they are sometimes not at all reliable.
I see.
But based on that, we observe something that is promising, the direction.
Okay. Yeah. The other thought was that blue score can be quite, it's an aggregate, it's a very crude measure, right? So one possible thing to check was, since you're talking about the semantic quality of the TTS, whether it's intelligible and so on and so forth, because that is what will affect translation, right? And so what I was wondering is whether you could look not just at blue score, but maybe look at named entities and a few things like that to see if they got translated correctly.
Okay, yeah.
Either with the human speech or even to begin with the text, because sometimes the machine translation engine may have difficulty with some entities anyway. Yeah. So that way you could see, they could make a statement about the intelligibility of content-bearing words.
Yeah. Yeah, that's a great idea. I think we will definitely do it. Thank you for suggestion.
Okay, thanks. Yeah, bye. Thanks.
Thank you, Natasha. Thank you, Baisam, for your presentation. So we'll draw to the second group. And the second group is about TTS for low resource languages. First of all, I would like to point out 3 points that in the JSALT that I saw. That are first in TTS that we saw yesterday with the EMMA groups and EMMA teams and play your part teams about realistic TTS. So for us, we are interested in other realistic cases, which is the low resources, which means that we have realistic data that we are processing with, in the case that we don't have access to enough data. And the second point that I would like to highlight is that what Sandy also in the open ceremony is about in the JSALT, we have many people from different countries and speaking different languages. So it's for us the opportunity to work on different languages and also what we call, I call non-high resource languages instead of low resource languages. And the third point, we are in group. As you can see, there is a lot of people are involved in our group. Means we are working for low resources with people that speak those low resource languages. That's why our group is in all languages that we tackle. We have people that are at their mother tongue. They are not linguistics, but they are. At least they speak well these languages. So we also would like to tackle some point. In fact, when we would like to build TTS for low resource languages, we have motivated with three scenarios, main scenarios. The first one is the community. Given community would like to have like TTS for their own languages. The second one is that researchers would like to have like benchmarking, and they would like to access to the dataset, tools, and some guidance to have like how to build this, study these cases. And the third one is that companies would like to target some markets, and they would like to have some guidance, hints, how to have evaluations, how to build, and from where to start. And in this group, we are first, as you saw with my SAM groups, that we will challenge the TTS evals, TTS4ALL evals, and also we'll challenge some architectures, and we will build our own datasets. Before going further, let me just give you like what is the challenge in when we speak about lower resource languages. First, and nonetheless, we don't have access to the dataset. When you find like all the architectures that are state-of-the-art architectures, they are trained or fine-tuned on hours and hours of data. But in the low resources, we don't have access to this data. And the thing that with the data, this data, if we have access, they're not high quality. The second one is that we don't have always the knowledge, linguistic knowledge. This is a big gap. We don't know phonetics, like we don't have like graph to phonemes. This is a big issue. And the thing that those languages around the world, they are written in different way. For example, Arabic, Bengali that we saw, it's written in different ways, not Latin written ways. There is also when we are in the community perspectives, we don't have access to the computational, like we don't have like hours of GPU or hours of CPU like to compute and to have this such a opportunity. There is also something that are particular for low resource languages. Most of them, they suffer from the diversity of speaking, the way that I speak in, but also they have this kind of what we can call code switching between their languages and the high resource languages in different domain or different cases. And the thing that I also with low resource languages, we can not have like, for evaluation, we cannot access easily for people that are assign the TTS output. Like we cannot ask every time that we have fine-tuned the model to ask people that are, oh, come on, can you assign our models? They cannot. I mean, otherwise, like you cannot have this thing. So there is also thing that the last point is that most of the models are built on a lot of languages, high resource languages like French, like English, Spanish, and so on. That's why it's challenging. For tackling this challenge, and having in this mind this, we would like to address something during the workshop. We address 5 points. The first point is that how we can give some highlights about how the corpus should be, okay, and how we qualify, because we have not a lot of data, but the few that we have, we should be ensured that it fit the TTS, state-of-the-art TTS system to have a baseline. The second point that is like from where to start. When you have like few data and you have like a bunch of the models, from where to start? Which is the architecture that we give us cross-language, some results. And the third one, will have the third one, can we adapt this model that it's the starting point to any languages that we have? And from that point, we also say that, yeah, okay, during this, what we call transfer learning, can we change the behavior of the model to achieve the better results for this particular language, for these particular cases? And the third And the fifth one is that how to validate this finding if we have some finding. And for the first point, my colleague Yannick will present our contribution. First contribution.
Hi. So before going to data qualification, I would like to share about the data that we have collected. So far we have 6 data, that is Kabyle, Tunisian Arabic, Sarawak Malay, Cuban Spanish, Bengali, and Central Kurdish, with multiple hours and different scripts and multiple sample rates. So going on to the data qualification, so as you all know, we are working with the low resource language, which have limited available digital resources. So as I mentioned, we have 6 data that are collected from real-world scenarios or multiple resources, such as the community recordings, conversations, controlled studio setup. So we would like to perform TTS training on all these 6 data sets. So what motivates us to do data qualification is that the standard random splits that we usually do not qualify the data. So pre-filtering the low resource corpora can reduce the outliers and misalignments. So we propose to do data qualification prior to the training of the TTS system to understand the quality of the data and to prepare the data to meet the certain quality and consistency of our TTS performance. So going on to our first approach for data qualification, that is the acoustic quality assessment and filtering, or we call it as AQAF method, for balancing trend and test distributions. So initially, this is our original trend and test splits. So all the data will undergo pre-processing and feature extraction, that is F0, duration, and text features. So moving on to our first filtering, that is to apply duration bounds. So the data that does not fit the requirement of the duration will be removed, and the rest will be kept. So for the remaining data, we will apply the second filtering, that is the duration per character filtering. So the data that does not fit here will be removed, and the rest will be kept. And then we will have the new qualified trend and test splits. So we will look into the case study of Cuban Spanish. So before the cleaning, we can see that the distribution are heavily skewed with a lot of outliers. So we can say that the test and trend splits are not well separated. However, after the cleaning, we can see that the outliers have been successfully removed and the distribution are more smooth, symmetric, and centered. So to conclude, we can say that the trend and test distribution are better aligned. Moving on to our second approach for data qualification is the signal quality assessment and filtering, or we call it as SQAF method. So first of all, we have the training data that we obtained from our first approach, and then it will undergo the signal quality assessment. So we will evaluate the training data using our TTS4ALL evaluation package, and then we will calculate the correlation between the evaluation metrics. So from here, we will focus on the signal quality to calculate the score for each WebS file. So once we get the score, we will sort the data based on the score, and then we will have 3 subsets, that is 100% data, 80% higher quality data, and 80% lower quality data. So all this data will undergo TTS system training. So by the end of this experiment, we will evaluate the performance of the TTS system. So we will look into the case study for Sarawak Malay. So far, this is what we observe. So in this table, we have highlighted the metrics that is significant to each of the model. So what we can see here is that all of the aspect of the metrics, that is the intelligibility, naturalness, and signal quality, have a significant impact on the lower 80 model. So these are some of the takeaways from our experiment. So thanks to the data qualification, we are able to understand the quality of the low resource language data before we designed the TTS experiment. And then we were able to assess the data using TTS4ALL evaluation package to prepare our TTS experiment. So for our future work, we would like to conduct the data qualification experiments on different data sets to get more insights and analysis on the data qualification experiment. And also we would like to investigate on the phonetic coverage analysis for the data qualification. So next I will invite Iman to... Yeah.
So if you go to the very first part where you were doing the filtering based on, even before this, yeah, this one,
Yeah.
right? So this makes sense. I don't know whether it's feasible to do, like, when people build, speech recognition, speech-to-text systems, nowadays, of course, we just throw everything in the pot and let it run. But for a long time, we used to do something similar, where we would take the speech and the transcript and some basic system and do an alignment, like a forced alignment of the, and then keep things. So is that common in, cleaning TTS data as well, or is that not used much? Do you have a sense?
Yeah, it makes sense that in the traditional TTS they are filtering out, because if you see early TTS such as Merlin TTS from University of Edinburgh, they are filtering for forced alignment to be ensure that you have alignment between the input and the output, like the acoustic features. For us, we do all this, we are forcing data to have homogeneous behavior to be sure that it's work for TTS, to be sure. Otherwise, because we have no enough data, if we take only the data just as it is, because the founded data, we can have some behavior that we cannot control. In fact, in this, the issue that with this approach is that we lose data by removing the outliers.
Yeah, of course.
And the thing that and we lose also diversity. Why we like to lose this diversity in TTS? When you have a lot of diversity, you need also a lot of data. And the thing that we would like to do is to reduce this diversity to be focus on the one, and we hope that this will help to quickly get in the right TTS.
Okay, I have another question. I think it's for you, which is, when you remove this data, did you listen to any of it to see that you were actually removing bad data, or you just removed it because, for example, if the duration was too short, could be that the text is only one word, like yes.
Yeah.
So did you check that you're throwing out really bad data and not useful data?
Yeah, we did not. So,
okay. Okay. The other thing I was thinking is, when you look at duration per character filtering, right? This will select for what I would call normal speaking rate. And if you wanted a more expressive TTS, if you had an example, suppose you had me saying, holy cow, that is just a few characters, but it's taking up a lot of space because I'm putting emotion and stress or whatever it is on various things. So I was just wondering whether you look at what you remove.
Oh,
and
no. Yeah.
It may be worth it, I don't know.
Yeah.
Okay, all right. Okay, thanks.
Yeah, you're right that for the last experience that we have for low resource languages, the people from first we are not looking for expressivity. We are looking for intelligibility first.
Okay.
That we are forcing to have some monotonic expressiveness, without very expressiveness.
Okay.
Yeah, that's why we are forcing somehow the data
Okay. I mean, the other idea, of course, is very helpful in the sense that it doesn't matter what you or I think of the data. If it doesn't give you a good TTS system, it's not good data. So the second part I thought was well motivated. You just build it, you measure it, and if it's good, you keep it. Okay, all right, thanks.
Sure. Thank you.
Okay, can you go back to the I think there is some the table about the I think this one. Okay, so character error rate, story, and MOS here means the UTMOS or some the Proximos. Okay.
Yeah.
Yeah. Okay. Then my question is this case is you guys use the percentage, so it may be fine. But I'm just curious about many of the Proximos is trained with the large resource languages, right? And then applied to the low resource languages. For example, the dynamic range of the scores may change or due to some overtraining, some kind of irregular behavior happens. I'm just curious about how do you guys kind of learn the practice of applying this kind of Proximos to such kind of low resource scenarios? Yeah.
For our experience, MOS is sensitive for languages, but also for the durations of the samples.
Yeah.
Like most of the TTS are between like 3 seconds if you see like Liberty TTS or other, like between like 4 seconds and 10 seconds. And the thing that's why also we pre-processing like to fit this first criteria. But yeah, of course, there are the sensitive of MOS for the languages is there. For this, we are using it in blind way. Like we are hoping that it's like relative weights, and we are not calibrating for languages, for given languages. We're taking as it is, and we are applying. But maybe Mason has some additional. He's the master of evaluation.
Okay, thank you. Just one remark. We had one investigation on this type of predictor mass. So here is the mass from SQUIM PyTorch. And we had one experiment when we try to fine-tune it to the data. When data is very little, we cannot find, and we lose all the generalization of the model. So we have one paper with Natasha on that one for usage of the deepfake detection adaptation to the new task, and it would come out in the SSW interspeech. But the idea was if we use it in blind way, as Arila said, it would be more reliable in the low resource scenario when we don't have enough data to fine tune it. But I agree, it's not, it's a laser point for exit.
Okay, thank you. Yeah.
Thank you.
No, I just had a comment for the presenters. For the sake of the YouTube recording, whoever is answering should be under the faculty sign over there or this side. The camera doesn't see that far.
Yeah. Okay.
So don't answer from over there. So come to the middle. Thank you.
Thank you.
So here it's okay. 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 So for this part, we'll be focusing more on the second question, which is what is the starting point? And trying to answer this question, we have created the TTS model recommendation engine. So our objectives were mainly to automatically evaluate multiple TTS model on a given data set. Once that's done, the engine will recommend the most suitable model based on the audio quality, intelligibility, and evaluation performance. As a short-term deliverable, we created a Python orchestration script that takes as input the data set. It runs the full pipeline to generate a report with all evaluation results and the recommendation model. So the process will simply to be, first we leverage data analysis, then we run the zero-shot inference. After that, we evaluate using intrusive metrics to finally recommend the model for fine-tuning. As a long-term deliverable, we aim to create a full-stack platform where users can easily upload their dataset and perform automated analysis and model selection for fine-tuning. And the process will be to leverage data analysis, then to calculate the similarity between the new dataset and all the datasets that we have worked on during this workshop, then to consider prior model performance on the most similar language. After that, we'll run the zero-shot inference and then to evaluate using both intrusive and non-intrusive metrics to recommend the model. So here is the overview of the short-term process. Starting from the data set, we analyze the data, the audios, by extracting the key spectral and prosodic features. Then we run zero-shot inference to assess baseline model performance to see how they will perform without any fine-tuning. After that, we evaluate the outputs using only intrusive metrics to do then the sample level comparison and to apply a ranking strategy to recommend the best model for fine-tuning. For the first step, here we have used the output of the work presented by Vadriani. So we will extract from the input audios the spectral feature and the prosodic ones. Then we will perform the automatic quality inspection of TTS dataset by analyzing the extracted features. After that, we will generate the plots that were presented by Vadriani for feature distribution, for example, the pitch, range, duration, histogram, and energy contours. This one is an example of the plot that represents the duration per second distribution for the Tunisian Arabic dataset. As a second step, we will run the zero-shot model inference, and we started with 3 architectures that we have chosen them according to some criteria, which are the language script support, the checkpoint availability and open source code, user-friendly code, reasonable resources, and architecture diversity. The 3 architectures that we started with are VITS, which is an end-to-end transformer-based non-autoregressive model. VITS jointly model the text, speech, and the latent variables to generate natural speech. The second one is the F5 TTS. It's a non-autoregressive diffusion-based model. It was trained on almost 100K hours of multilingual data. Its base version has around 158 million parameters. It's heavy, but it's a state-of-the-art model. The third one is the XTTS, which is an autoregressive multilingual model trained on almost 27 hours across 16 languages. It uses a VQ VAE encoder, GPT-2 as a decoder, and HiFiGAN as a vocoder. For the third step, we have the system evaluation. As I already mentioned, currently we support only the intrusive evaluation metrics, which are the MCD to measure the spectral distortion, the BAP to capture spectral characteristics related to the noise, the VAV error to assess the silence prediction correctness, and the LF0 error to evaluate the pitch accuracy. As a future support, we will also add the metrics that were presented by Massam and Natasha to measure the naturalness, intelligibility, and the signal quality. So now that we have run the data analysis, the zero-shot inference for our 3 architectures, and the intrusive evaluation, we will do a sample level comparison. So we start by normalizing each metric to a 0 to 1 range. Then for each sample, we calculate the total score. Here, the score is simply the sum of the normalized values. And for all the metrics, the lower is better. So for our score also, the lower is better. After that, we identify the best performing model per sample. So for each sample, we will determine which system has the lowest total score. As this simple example, for this audio, the best system is XTTS because it has the lowest score. After that, we count how many times each system was the best across all the samples to finally apply a ranking-based system recommendation. Our ranking here is using a simple majority vote strategy to select the best model, and this one will be recommended for the fine-tuning. As a future improvements, we will add other state-of-the-art models, and we will add weights to metrics. So instead of calculating just the simple weighted sum of all the metrics, we will add the weights, and the weight will be according to the importance of each metric. And we will add also the non-intrusive metrics. Okay, so now once we have created our first version of the engine, we wanted to test it. So we started with the Tunisian Arabic data set. We gave it as input to the engine, and this was the result. The engine recommended to fine-tune F5 TTS with the following ranking. F5 TTS as the best model, then VITS, then XTTS. After that, we wanted to validate our approach, so we did fine-tuning and post-processing. So all the 3 models were fine-tuning using on the train set. After that, they were evaluated, and we have used the same ranking process to obtain the results, which are the same ranking confirmed. So the F5 TTS fine-tuned gave the best results, then WITS, then X TTS. So in this case, the recommendation engine aligned with the post-fine-tuning results, but we need to test across all the other languages that we are working on and other models to just validate the approach. The code of this first version of the engine is available now on the Liam GitLab, and it will be publicly available. That's all for me. Now Anna will be presenting the transfer learning part.
Thank you, Emin. Well, with all these recommendations on mind and with focusing on leveraging the possibilities that transfer learning give to us, using fine-tuning and zero-shot adaptation approaches, we'll try to adapt all possible available TTS systems to new speaker, language, accent, using limited voice data. I'll just show some insights about the fine-tuning process, specifically for F5 TTS, which ended up being our golden standard. As Iman said, it's a flow matching model based on using diffusion transformer that doesn't require like complex design model like duration models or phoneme alignment. It just takes the text input, it's padded with some filler tokens to the length of the reference audio, and then the denoising process, it takes care to generate the audio. To see how the learning process affects the intelligibility, I just brought 2 examples of 2 of the languages that we tackled during the workshops, is Kurdish and Cuban Spanish. We can see that for character rates, which means the accuracy, the error of the predictions of the transcripts, and the STOI metrics, which measures the acoustic intelligibility, both models show consistent and effective intelligibility learning. But starting from, we can see also that starting from a closed language checkpoints, as is the case for Cuban and Spanish, it determines how fast the model gets to bear intelligibility. We can see how for the Kurdish, even though it has 10 hours of data for training, it takes some iterations to achieve a character rate that the Cuban Spanish has even in the earliest stages of the learning. And in the case of naturalness, it's also affected by the fine-tuning process. The models achieve high naturalness, but potentially at the cost of some signal quality. At least is what signal quality metrics show. But of course, we have to take into account that these advanced generative models are built to optimize the naturalness and the expressivity of the synthesized voice. And these quality metrics may hide or may sometimes also penalize this characteristic that the model is trained to obtain. And also some interesting insights about the MOS behavior that we saw that for Kurdish, for Spanish, also for Sarawak Malay, you can see some local minimums of the functions on the same iterations values, may be related with some learning phases of the model, optimizer schedules, and so on. So far we have invested time, we have invested computational resources trying to fine-tune these models, but we really need to see where their strength is and when can be the potential risk of the system that we already have. And of course, as we have been seeing, the standard evaluation is like a snapshot of the situation, but they don't provide a comprehensive tool to analyze and to decide in critical situations. That's why we came up with a controlled experimental design, which in its first steps, it's a representative data creation step when we prompt LLM to generate 5 challenging use cases for each system. I'm talking maybe referring more to the Cuban Spanish, which was the language I used, but we used this protocol for all the 6 languages that we were working on. And we used the same prompt for all the languages. the prompt were trying to achieve one of the use cases would be character coverage. If we prompt the model to generate some utterances where they cover most of the characters of each language. Also, semantical unpredictable sentences that grammatically are correct, but they have not meaning. Code switching, some sentences with different words of different language, language-specific vocabulary of each region where these languages are spoken, and prosodic variation, meaning sentences that can be spoken in a wide variety of ways. All of these sentences provided by the language model were selected by native speakers. And also with these sentences and the results of the TTS we obtain, we compute the validation metrics. And I just brought this example of different character array, the fake major, some quality signal major, just to show how a same model can behave different on the different use cases scenarios. The light green will be the generic sentences that we have from our test sets, and the others is character coverage, sentence unexpected, language-specific vocabulary, process variations, and you can see, for example, how tough could be for the Cuban Spanish model to recognize characters in the prosodic variation test case. So this can help us to answer how good is this model, what is it good for, and where it needs improvement. But of course, we try to take profit of that we are together, that we have a community behind us that could help us to do some perceptual evaluation. And as Ahila said, we have launched a web platform where you can you can help us to decide, to qualify some samples of the different language that we've been using. Of course, if you feel like comfortable in one of them. So far we have, I will present like these preliminary results for the Cuban Spanish, where we already have more than 8,000 evaluations made by 18 listeners. And I didn't brought, but it was really low, the correlation of this MOS with the MOS brought by the metric computed with this estimated. But here you can see that also humans agree that the prosodic variations is very, I mean, our model lacks from that kind of information, and also they help me to see how character coverage also could be, I mean, it could be a strength in the training process to obtain a more solid system, more robust system. So far in the group we have come with bunch of fine-tuned TTS models from different architectures. Also zero-shot model tested for over the 6 low resources language that we work on. We have evaluated all these models with the evaluation package. So every of the language are evaluated with the same tools. We came up with multilingual use case driven test sets, and we are conducting a perceptual evaluation with a potential TTS multilingual corpus coming out of it. About the possible of modifying the model. I don't know if you have some questions. Yeah.
So it's more like a clarification. The perceptual evaluation here means you conduct a subjective evaluation, or? Subjective. Okay, and then. Yeah, go ahead.
Sorry, you asked if there's a subjective evaluation?
Yeah.
Well, it's a perceptual evaluation, yeah.
Okay.
It's about quality of the signal. We just ask the people to qualify if it sounds human, less human, more.
Sounds good. And is that the crowdsourcing based, or just kind of asking your
It's a web page. We ask our communities I mean, as the people from Cuba, Sarah from the people from Malay, so they are helping.
Sounds good, very cool.
Without paying.
Yeah, and then my question is actually, do you check whether this person really know this language?
No, if we check if they are doing a good evaluation.
Yeah, so my experience is that the, like for example, English speaker evaluating French speech, and then it's actually, you know, that sounds kind of French, and they have actually high score, but it turns out that it's a kind of mix of the quality and the intelligibility. But anyway, that kind of situation may even happen more in the multilingual low resource scenario.
Yeah.
So I'm just curious about, is there some protocol to find, you know, good?
So far we have, I mean, in our cases we have shared only with a community that is responsible, that we know they're going to evaluate only their mother tongue. And I don't know, maybe to release it, it would be important to take, I don't know.
I see.
Thank you so much for pointing out this information. It's, I think that we can, if I understand well, like it's about the metadata about listeners, like we are collecting the data. So far, we're not doing that. It's like there is a lot of there is a lot of factors we are not controlling. The thing that it's like the way that it's listening, the listening is behaving, like the behavior of listener, but also the conditions, like the conditions. And also the where he's like if he like, for example, we'll take some condition, like if the speakers, like the native speakers, but his daily life he's speaking other languages, maybe this can be different. The way that the expectation is different.
I see.
And for low resource languages, most of the time, the expectations are very high because of the oral languages. Most of the time, the prosodic information is the expectation is very, very high. That's what we saw. For example, for Cuban accents, the expectation for prosody is there because the prosody convey a lot of information that in the native languages is not there. Which means that this is challenging, and we have to analyze this. For now, the problem with the subjective evaluation, more you are constraining the listener, more you're adding more, like you're asking more information, more like you are losing listeners, and it's very hard.
Yeah.
For instance, we keep it simple. The idea is to collect and then to analyze the information. As we collect for 6 languages, we extend this for other languages, and then we analyzing is keep it simple is the I think that for us it's the easiest way to handle it. Thank you so much for your question. Thank you so much. Yeah, for our coming presentation, Gabriel will have, so far we are using transfer learning, like it's just that we are transferring for higher source of like models that are trained on a bunch of data, and we saw that it's like, okay, it's work, but we don't have, during this fine-tuning way, we don't have control. We don't have control. Can we add more information during the fine-tuning without destroying the information that we had before? Thank you.
Thank you very much for the introduction, and thank you everybody for this time work in JSALT. Then beginning with the same problem in the classical synthesis problem, we have low result data. We need taking account the speaker accent, and we need introduce the intonation sentence in this process. For us, the intonation sentence is about the interrogative, exclamative expression. For take these 3 information in the same process, we select the E5 model because it's an excellent cloning voice, and this model has as input the accent, the speaker accent, and the text content. Then we need a way for use the intention information. For this we use the signal control inside of the diffusion block The idea is use this signal plus the information intonation. Here we have another problem. The information intonation, we need to create this embedding for this. Then for obtain the embedding about this intonation, use the fair way in reality, use the speaker recognition framework, using ICAPA-TDN for obtain the common speaker information. Of course, in our data, we have only one speaker and the same language, and we obtain the mean embedding of all the database. We have the common information in our database. Then and subtract this information for each set sentences. For example, we have 4 sets: interrogative set, exclamative set. Then we remove the speaker information. We have only it's not only, but we have the interrogative information for this set. This is the idea, and use the mean of this for each set. I have the embedding information. And finally, use the objective metrics of our Mason group. What is the idea? We prove 3 models. Zero short E5, of course, in Spanish. Fine-tuned E5 for Q1 in Spanish. And our approach is the fine-tuning the E5 plus the intention information. Then we achieve the good result. Maybe it's not the end of this research. We need to take more information for proof our approach. In this moment, we go for English database for take some experimental for say this is good, or maybe more mathematician proof for this. And finally, Ahila said some conclusion of this part of the work.
Thank you so much, Gabriel. I think that we are out of the time. Sorry for that. I will try to be fast. For outcoming, I think that we find some things that are data sets. Also, there is the thing that we have also. We will upload also the on the Hugging Face the model, the fine-tuned model for the different accent, code switching, and situation for other languages that we have, and we are also have some hints about from where to start for given languages, and also have we have primary results that our models can be flexible during the fine-tuning size. And we launched some listening tests, multilingual, which is good. I think that for a short term, we can say that we are going to extend for languages that initially we targeted, but we don't have experts. African languages like Iwondo and Yemba, where we have sometimes few words recorded or few sentences, which means we have a few minutes. And then we have also our engine that is recommended one architecture. We can go on, and we have we can follow the same steps as we saw in mixture of experts. And there is other, for transfer learning, there is a bunch of techniques that we start, but we didn't finish during this workshop, but it will continue, introducing LLM for giving more context, more informations. And the good thing that we have with the listening test that we can also have multilingual predictor of the quality. I would like to thank all my colleagues. Thank you so much for your presentation, Gabriel, Mariani, and Anna, and Iman. And that's it for this before coffee. Thank you so much. Thank you.
Welcome back from the coffee break, sorry. I tell you. So I'm going to introduce the prosody group and to tell about what they are going to talk about. Okay, so first of all, just a quick recap. What we call prosody is when we have an audio and you extract all the information related with the speaker, the prosodic, the channel effect, and what is left is what we call prosody. And it mostly represents an tag like emotion, accent, intention, and so on. And for that, it mostly uses energy and pitch to be represented. So most of the TTS systems are designed using huge amount of data, and the problem is that in the low resources scenario, this data doesn't contain enough variation of the prosody. So probably this will lead to a mismatch between what the model learned and what we want to have as a result. For example, in Spanish, for different dialects, the same sentence will change a lot the prosody. So this is the low resources tag that we need to take into account the prosody in the TTS system. So because of that, we split our work in 2 branches that they work parallel during the workshop. One of them is to get a prosody embedding extractor that is agnostic to tag, language, and speaker, and also contain only prosody information and not other information like the speaker and so on. On the other side, we have a developed TTS system that allow us to put as an input the prosody representation that we have. And not most of the TTS system now use that have prosody control. They use also the speaker information embedded there, so we want to separate this part. Another motivation for having these 2 branches is that most of the TTS systems that have prosody control use a representation that was trained with some data that when you change the tag, you have to train a new representation of this embedding. So because of that, we wanted to have a prosody representation that is not conditioned by the tag, because on the low resources scenario, do not have amount of data to retrain this representation. So Martin will talk first about the first branch, that is the prosody embedding extractor, and then Santi will talk about the second branch. So I will pass the microphone.
Thank you, Lara. Hi, everyone. Okay, I will talk a bit about the prosodic representation that we built during this workshop. The first, I want to talk a bit about the prosodic features, because we need to do a certain step for preprocessing in order to obtain this kind of signals. The first one is regarding the segmentation. Usually, we use a voice activity detector to and applying some criteria over the silence duration in order to segment the data. When we have like more conversational data, this system sometimes fails, so it's a thing that we have to be carefully using that. And then we extract the energy signal using the and apply some filters in order to match with the human hearing, with the way the human hear the audio intensity, and we call this loudness. Then for the pitch, we have to extract the F0 signal. There are many algorithms to do that, and the best choice usually depends on the quality of the data and also on the type of the background noise that we have in the data also. The F0 signal is a non-continuous one, so we have to do something with the non-voicey segment. A common approach is to do an interpolation over this segment, and also we only want to keep the slow variation in the signals because we care more about the, we want to do an analysis at the utterance level, so we are, we want to have the intonation information and discard the variation that, that has more to do with the specific phonemes in the audio signal, so we also apply some filtering. Once we have these signals, we train this sequence-to-sequence autoencoder in order to extract the representation. In this architecture, the encoder basically tries to compress all the information present at the input features to one fixed size vector or fixed size embedding, and then the decoder is trained to reconstruct the input signal only using this fixed size representation. So in this way, we can think of this embedding as a summary of all the prosodic patterns that we have in the input, and as Lara said before, this representation is training to reconstruct the pitch, the prosodic features, and not for any specific task. So we can then use this for multiple tasks. Once we have that, we do some experiments to assess the quality of the representation. For this experiment, we take 3 databases from WP0 and also the data that we use to train the model that is in English. And we wanted to see if the performance of the system is the same across different languages. So in this plot, on the top, you can see that the distribution of the duration across the data sets are not the same. And also, as we expect, there is a clear linear relationship between the length of the input feature and the reconstruction performance. That is because the longer the sequences, the more information that the model have to encode in the same size embedding. So if we want to see if there is difference between databases, we have to look only on a specific segment of the x-axis. If we do that and take segment on the x-axis, we can see that for all the segments in which we have enough data for the 4 databases here, there is no meaningful difference between the reconstruction error over the different databases. So we can say that the representation is agnostic to the language. And we have do the same experiment with many other databases in the WP0, and we find the same behavior in all the cases that we have good quality data. So we can do a similar experiment, but looking for the speaker variation. And in this case, we train the model with a mono-speaker English database and then test it with a multi-speaker English database. And in this case, we take all the samples following the same time distribution, so we can directly compare between speakers. And here we can see that also there is no difference between the performance for different speakers. So the conclusion for that is that we don't care about the language of the speaker. We only need to good quality data, and the more expressive the data is, the better for the representation. Finally, we have to comprove that the embedding have the information that we want to encode. For do that, we think of this experiment that we choose to do emotion classification. We know that the prosody is important for the emotion classification, so we compare our embedding with the EGMAPS feature set that is a commonly used feature set for this task. And as these features contains not only prosodic information, but also spectral and formant and many, many more, we also compare with a subset of this EGMAPS feature set that only contain F0 and loudness features. And we do emotion classification over two databases, one in English and one in German. So the result shows that our embedding are informative, are better than the random guess, and performs not too far from this EGMAPS feature set. And this is the case for the two languages, showing cross languages robustness. So with all this experiment, we can say that we have an util prosodic embedding extractor. So the next step is to talk about the TTS system, and Santi will talk about that. Yeah.
I should have asked this earlier. If you go back to your figures in the beginning, keep going some more. Yeah, this one's good. Yeah, okay. So, you know, you have two-dimensional features. You have the energy contour and the pitch, right? But the pitch is not defined everywhere. So what do you do with frames where there is no?
In the end, in the final model, I have more features at the input because I found that it's not enough just only to put pitch and energy. What I am doing now is to put the interpolated version of the pitch, so it's a continuous signal, but also I put the sequence of voice and no voice segments to have also the information of the switch rate, let's say.
Because that's exactly what we found when we were doing pitch for speech recognition, that the probability of voicing was very useful.
Exactly. So in this case, the decoder is not only predicting the continuous curve, but also has a classification head to know if for a given frame is a voice or a not voice segment.
Okay. Then in that case, in your loss, do you reduce the penalty for?
I run many experiments to see what is the best way to.
Because in an unvoiced region, you don't want to penalize for getting the pitch wrong, right?
Yeah,
okay,
for sure.
That's one. The other question I had was later on in one of your results, you made a claim that it doesn't matter what kind of things you have, as long as there's a lot of pitch variation and energy in the data, you don't care about language. Right? Because you're saying somehow you learn how to represent pitch contours. But what if the languages were tonal? Then the tone is performing a different function versus a non-tonal language where pitch has. So would you still stand by your claim?
Yeah, you are completely right. I have to mention that we try almost with non-tonal language. That this conclusion is right for non-tonal language. I don't know what will be the case with tonal language, but maybe you are right. Maybe it is not the same situation because the role of the prosody in that language is not the same. So.
Yeah. And by the way, I'm not saying I'm convinced that it won't, or it will be different because
me neither.
For all I know, all you need to know is how pitch varies and how the human mouth can vary pitch, and that may be all you need. I don't know. Okay, thank you.
Thank you.
Other questions? No. Okay.
Hello, everyone. I'm planning to explain the part of TTS of our work package. As a recap, we decided to choose the KNN TTS model. That is a zero-shot TTS model that is composed by two branches. The top branch is an acoustic feature extractor that extracts the embeddings from the CEST layer of WFLM. While the bottom branch is like a natural TTS model that tries to align a test to an acoustic feature that is the WFLM layer. This model also has a lambda parameter that tries to control if the model has to take into more account the reference speaker, is to say the low TTS speaker, or the target speaker, that is the WFLM speaker. As first experiment, we try to know, to compare how this parameter or how it affects the model if we change the target speaker on the pitch contour. In this plot, we train a low TTS model on one male speaker of male labs, that is a Spanish mono speaker, and then we use several speakers as target from Albaicin Spanish database. In this experiment, we use female voices and male voices, and we can observe that the pitch contour and the intonation patterns are so similar in each experiment. Although the pitch values vary, for example, the female voice has higher pitch values and the male voice lower values, we saw that the difference on prosody, there are so locals and in short terms, for example, like AV curve on 6 seconds or something like that, but there is so conservative. So we decided to use this model because it's simple, modular, and we can also incorporate more modules and interpret how it goes. Also, as the last plot, we saw that the target speaker branch is more conservative in prosody change, so we decided only to study how the glow TTS model affects and how we can control the prosody inside the glow TTS model. The glow TTS model is a normalizing flow model that tries to generate acoustic features from a text embeddings as input. We choose this model because it's a lightweight model. It only has 55 million parameters counting the glow TTS and the hi-fi GAN model, and we can train easily this model. It also has an alignment and a duration predictor that makes the model not autoregressive, so they have a faster inference, and we can control and interpret what is happening inside this model. If we want to know what is the prosody information encoded inside the model, we assume that the duration is encoded on the duration predictor and the alignment. The pitch intonation is also encoded of the WAV-LM features and also in the alignment because it's important the duration of each phoneme, and the energy is only encoded on the WAV-LM features. First of all, we decided to train 3 models on single speaker, one on a Spanish single speaker, another with Argentina single speaker, another with a Mexican single speaker. But this model have a problem, that is they have a deterministic duration predictor, so each phoneme have always the same duration. In this plot that is obtained by on the BIS paper, we can realize that low TTS always have the same duration from each phoneme, so this is not natural because when we are talking, each phoneme have different duration or different, and it also affects on the prosody curve and the control of the pitch. So we decided to change the duration predictor for a stochastic duration predictor that is extracted for the BIS model and obtain this first approach, only changing the duration predictor. We train another model with the stochastic duration predictor using both 3D speakers, and then we try to include an implicit pitch control. We saw that paper from Ogun, that trying to use the same module as the stochastic duration predictor by trying to predict the pitch of from the test embeddings. They expand the test embedding using the predictor of the duration, and then you can use the pitch at the decoder part to condition the output. In our first experiment with this model, the pitch prediction is not so good, but it can estimate a little bit the component of the output. And nowadays we would like to include the prosodic embedding that Martin extract on these stochastic modules and also on the decoder, try to obtain or give more information about the prosody to the model to control it and obtain output that could be more rich on prosody level. This will be our first, our final model, but we have some problems when we were extracting the embeddings, and we take more time than we expected. So this work is also in progress. We obtain a lot of outputs, but nowadays we are training the final model with the prosodic embeddings, but we didn't obtain any results yet. And also, we have the problem of the evaluation system, because we have the TTS4ALL metrics that was defined by Mason Group before. But these metrics are not good trying to measure the prosody, because they only use the pitch variation, and it's not a robust metric trying to know if the prosody is being changing good or not. So we decide to use the TTS4ALL metrics to define or to choose what is the best checkpoints in our training, but I think that we need a robust metrics to evaluate it. For example, we decide to use task classifiers depending on the function that we would like to change the prosody. For example, it could be like accent or emotion, but this is in progress. So the next steps will be like finishing the last TTS model trained on prosodic embedding vectors, and start to design the evaluation protocol to know if our changes of the prosody is going correct or not. This is our first stone on the trying to evaluate this prosodic, and we define this metric that it could be task agnostic, for example, comparing the distance between the prosodic embeddings, or gross pitch error or voice decision error. Also, a subjective evaluation like recognition the accent, but it will be more costful. And also, our main idea is task-oriented evaluation, that is evaluate depending on the task that we would like to change the prosody. And also, we will plan to publish the models that we have trained and the code once we finish all the experiments. And with that, we finish, and Yannick will present the next part.
By the way, others are free to ask questions as well. I don't have a monopoly on the mic. Right. So if you go back to your, keep going back. Yeah, stop here. So I didn't understand something. So you said that you're trying to predict the F0 as well. Okay, so one question I had was, why, like, instead of going after log F0, you said you didn't have a lot of success with this, right?
We obtained that idea from the paper that is mentioned here, but it's only try to have an implicit model to extract the pitch, but I think that the prosodic embedding, it will be more richness than this model.
Yeah, one thought I had was that, sometimes absolute pitch is hard to predict because there's a lot of variation, but also from a communication point of view, it's the pitch changes that are more important, right? So would something simple help you, like instead of saying log F0 is your target, you do something like find the min F0 for that speaker, and you do log of 1 plus F0 over min F0. That way you're just looking at the relative change in F0 compared to the minimum for that speaker, and you add a 1 to make sure you don't get too close to 0 or something like that. Okay. Or something. I don't know, that's just a thought. Yeah.
We can try that.
Also, during training, this system is mono-speaker, so you will have only one speaker, so maybe estimating this mean value.
That's true. If you have only one speaker, that's different. Yeah. But even for one speaker, though, sometimes, like, if you're excited, the whole baseline moves up and, like, things like that. Yeah. Okay. Yeah, if it's only one speaker, I agree. It won't make a big difference. Yeah.
We have a lot of variability.
Okay.
But we have to.
All right. Other questions? No? All right.
Thank you. So now I'm going to talk to you about another part of the work that was dedicated to Noel codec especially for TTS applications. So the main contributor of this part was Salima, but she has to leave last week the workshop, so I am making her presentation. But there is also, of course, Tianping and Fethi, who were involved in this work. So why we want to work on the neural network? Well, what are the qualities? So first, it's very useful to construct very efficient speech representation, especially discrete representation. Nowadays, there is already some works that started using this kind of neural models in order to combine both speech and text modalities for large language models. And also we know that there are some opportunities we would like to investigate in this kind of model. For instance, how to control them, how to control the voice that they generate. And also there is some interesting architectures now that could help to get streaming TTS. It is what we want to investigate. So there are 2 points, two main objectives we have, two main targets. The first one is about low latency streaming. So for TTS, we would like to get this kind of TTS on streaming. For instance, when we want to put on the top of a large language model that generates only text, we would like to be able to sensitize the speech on the fly in the same way, in the same time as the text is generated. And also, we would like to work on pseudonymization. That is an application that consists in replacing some words from speech in order to with other words, especially sensitive words. When, for instance, if you want to protect some privacy, for instance, to respect some European content from the European regulations, like the GDPR. Or also, it could be to hide some information given by children when they submit some vocal messages on social networks. We want to hide the name, the age, the address, or something like that. And also, it could be useful for witness protection in trials. There was different neural codecs we could use for this work. We studied different neural codecs, and there is one we wanted to focus, so we focused on it. It was the TAI codec. So the TAI codec is a neural codec that is inspired from another neural codec that is called Hi-Fi codec. So the TAI codec is an evolution, if you want, of the Hi-Fi codec. I will present some more in the next slide, what is Hi-Fi codec and what is TAI codec. So the main interest of the TAI codec is that the author of this architecture introduced a time variant token that has objective to capture all the invariant information all around the time, what is redundant in the speech signal that could be captured by a unique token in order to make the compression more efficient, the compression in the sequence of discrete speech unit. And we wanted, this first conception was to port this neural architecture within the SpeechBrain project. We are a contributor of this project, and we use it for research daily, and it's very useful to get this kind of neural codec in a such tool. So this is the architecture of the Hi-Fi codec. So I think, yes. Here, this is an encoder made of convolutions. So we have an input, audio input, and we want to reconstruct it at the end. And the objective here, we want to compress all the speech signal here into a sequence of discrete speech units, speech tokens. And by this way, they apply an encoder to generate a sequence of latent speech representation, a continuous representation. And after, there is a RVQ, a residual vector quantization, that is applied on these continuous vectors in order to get some quantized vector from 1 or to 4. They use 1 to 4 code books in order to generate this in this architecture. What we know see that what is important here is that the entire audio is proposed as the input of the encoder, and the entire audio is generated during the training process. Okay. So now, what happens? What is the novelty in the TAI codec, neural codec, is that they add this module. This module will generate a time invariant codec in addition to this discrete speech codec, this sequence. The idea is that this time invariant token will capture the invariant information. So for now, we didn't know which kind of information. It's something we studied during this workshop. It will be one of the topics of the next presentation. And so what we can see is that there is this module that is extract the time invariant representation, and this module is plugged after the second block of the encoder block, okay? And so the two first blocks construct the speech representation for both the discrete speech units, the sequence of discrete speech units, the usual one, and the time invariant token. During the training process, it is not the entire audio file that is provided to the neural codec, it's just some chunk, some segments of the audio files. So for instance, if I want to generate during the training process only this part, the first segment, you can see at the output it is the same input segment. We will select randomly another part of the audio signal. And the idea here, in order to generate this time invariant token, is to extract the information that is exactly the same in segment 1 and the randomly selected segment 2. This is here, they added a new loss in the training process. That's why to maximize the similarity between the two representations that represent each segment, okay? So that's the main novelty. And just to have a zoom in this entire module, it's something close to the first implementation to extract X vectors, so the convolution 1D, and the use of statistic pooling. Okay. So we implement this architecture into the speech brain project. So now it is available. It will be available. It's not yet available because the official integration will be a little bit long because there's different processes to respect. But it will be very soon, I expect, available for the speech brain community, for all the people that want to use this. It's this answer to this implementation, long-term maintenance, and a lot of facilities like the multi-GPU management. We also trained some models with the English and the Libre TTS corpus, like in the original TAI codec paper. But also we made some training with multilingual data, but we didn't have time to investigate what we could do with that. It will be the next steps of this work, one of the next steps. So, as I said just now, the TAI codec, neural codec, is trained chunk by chunk, but at inference time, it processes an entire audio file, okay? But we would like to see if we could use the way it has been trained in order to use it in a streaming way. It was one of our objectives. So, just to recall, I simplified the architecture here. So I want to regenerate the green part of the signal. At the training time, they do that because they need to get two different segments in order to capture what is constant, what is invariant between these two segments. during the training process, there is a lot of randomly pairs of segments that has been selected in order to capture what is common. But in the same way, we want to regenerate only the green part. At inference time, it's all the entire input file that is provided to the neural codec, and that's all. So what we tried to do is to use at inference time this chunk by chunk capability. So we generate the audio file chunk by chunk without any context. We just use the context of the chunk to generate the same part, and at the end we concatenate the audio to get the final result. And we made some tests by using some metrics that are dedicated to measure the quality of the signal that has been reconstructed. And we could see that when we use as inference mode the normal way or the chunk-based way, we have very similar results. So it's not so. That means that it is very interesting to continue working on this part, on this way, in order to get TTS. So yeah, I would like to make you. Okay. Sorry. This is the natural voice, the original voice.
To all appearances, very good health, and they left by early train for London.
This is the reconstructed voice by the common way, the original way.
To all appearances, very good health, and they left by early train for London.
And what we get by just concatenating the chunks, we regenerate independently. Sorry.
To all appearances, very good health, and they left by early train for London.
Well, so it's not perfect, but it sounds good, and also what is important, I didn't mention that, but at the beginning, that we use some neural codec that can be used by academic people, academic researchers. We don't have access to 1,000 hours of speech, and so we compute this only with less than, I think it's around 500 hours of speech, the training of this dataset in English. So we made also some experiments in order to check if we can do better. We have still some experiments in progress, but the only one we had time to finalize before the end of the workshop was to try to use variable lengths of the chunk during the training process, because originally the chunk size is 660 milliseconds for each, so it's fixed, and we change to vary it randomly. We also, in what we have in progress now, we changed the size according to some word alignment we have on the signal, because at the end what we want to do is to transform text into signal. So we would like also to take this linguistic constraint in order to improve to get a TTS and summing. So for now we didn't get any result by applying this random size during the training process. So the next steps. So we are working on text-to-speech token conversion, Tenping and I, for instance. So we have some work in progress. We didn't have very nice result for now. We continue working on it. Something we would like also to do, because it is important probably, is to be able to condition, especially for pseudonymization. You know, we want to modify the voice, some words in audio recordings, only some words, but we have all the information about the prosody, the speaker, and so on. So we would like to use this information captured by the time invariant codec, for instance, to generate the relevant discrete speech token that are used by the time codec decoder. Of course, we want also to get a text-to-speech token that works on streaming, on the fly, if we want to get this swimming TTS, it's mandatory. And also we want to control the voice we generate by playing with this time invariant codec we want to analyze, but we need to better understand which kind of information there is in this time invariant codec. So as a conclusion, we had now a clean version of the Thai codec neural codec in speech brain. The models will be released very soon in Hugging Face. Maybe they are already, but I'm not sure. We showed that it is possible to use this Thai codec model in a streaming way without a loss, an important loss of performance. And also, we know that we have still work to do. GraphM to text GraphM to speech codecs, and we also have to better understand which kind of information is the Thai codec, and maybe we can do better. And it is the topic of the next presentation. So I'm giving the floor to Kélian. Maybe, except if there is some question. Maybe later.
So, good morning, everybody. So now I'm going to present you our work about the speech representation analysis and reconstruction performance. So that work has involved Luca, Michael, and myself. So our motivation was about to work on the T codec because of its ability to achieve a high-quality speech reconstruction with fewer tokens. So what is interesting in this kind of architecture is the use of the TIRE module. So the TIRE is the acronym of time invariant representation extraction. But at this moment, we didn't know really how the TIRE encoded and represented this kind of information. So that was what our work is about. So here are the three main objectives for our work. So the first one is about to analyze the time invariant features by proposing a layer-wise analysis of time invariant features, and to be able to probe the information included in time invariant features. So the second objective was about making an investigation of the different segment level strategies. And the last one was to propose a new architecture of the T codec thanks to the knowledge that we will learn with the previous experiment. So now let's see the methodology that have been used during the works. So we have used the T codec with the 4 frame level token configurations. We have trained our model on the Libri TTS dataset that is a subset of the Libri speech corpus, so English reading books. We have trained the model on 250K iterations on only on English speech, ensuring a monolingual codec baseline. And for the testing protocol, we have tested our model on in-domain reconstruction performance, so on the test clean split of the Libri TTS, but also on out-of-domain reconstruction performance like the VCTK, that is a dataset about different accents, and on other languages like German, French, Japanese, and Korean. So the evaluation metrics that we have been used are the VSCOL V3, the PESQ, STY, MCD, and similarity speaker. So here is our first experiment about the layer-wise analysis. So basically, on the original recipe of the decodec, we are extracting the representation from the second layer of the encoder and inject the result into the second layer of the decoder. So what we did is that we have tried to extract the representation from the first layer and inject them into the third layer of the decoder. And we did that for the first, second, third, and fourth layer of the decoder. So the main purpose of that was to analyze, to make an investigation of the impact of TIRE on feature propagation, and to see how it contributes to improve speech reconstruction. So here are the results. So as you can see, for the PSQ, STY, and MCD metrics, we obtain the best result when we are starting the representation from the second layer. But for the viscol and similarity speaker metrics, we obtain the best result when we are starting our information from the third layer. So that seems to suggest that different layers encode distinct types of informations. So now I'm going to let the speech to Michael.
Hi. So at this step, we know that feature time invariant capture stable information across along nodule, but we don't know what information are encoded in time invariant features, and we don't know which layer of the encoder provides the most information for the tier. So in order to answer to this question, we propose to use time invariant features as a classifier input for some downstream tasks, and to use metric, by example, like accuracy, like an indicator of how much information is including in time invariant features. So for downstream task, so we propose to use 5 tasks. So speaker identification, that consists to identify a speaker; acoustic scene classification, that consists to identify scene, by example, if an audio is recorded in a metro, park, city, or something like that. Emotion classification, that consists to identify the emotion of speaker, like, by example, joy, anger, fear. And language classification, that consists to identify if a speaker speaks in French, Italian, German. And the last downstream task is spoken word detection, that consists to identify a word in audio. So in order to do that, we use a very simple deep neural network with 2 hidden layers, and we propose to use time invariant features of an audio segment and to use like metrics accuracy. Sorry. So the figures summarize all the experiments. So each group of the figure is a specific task, and each bar is a specific layer. As the different task has different number of output, different number of classes, we propose to add dot line in dark that correspond to the accuracy obtained by uniformly assigning sample to a class random, and this dot line in black gives the possibility to compare the different tasks. So concerning the information encoding in time invariant features, we observe that acoustic scene, emotion, and speaker content are very well encoded in time invariant features, but language and spoken and semantic content are not well encoded in time invariant features. Concerning the layer-wise analysis, we observe that the layer 4 encode no information, but the layer 1, 2, and 3 capture nearly the same level of information.
So now let's see another experiment that we did that was about the analysis of segment level selection strategies. So on the original RIS IP of the DIC codec, we are choosing the 2 segments randomly. So we have proposed 4 new ways to choose them. The first one is random non-overlapping. So when we are choosing the segment randomly, but the second one doesn't have to overlap on the first one. The adjacent segment strategies. So when we are choosing the first segment, the segment that is directly following will be the second one. The cross file with the same speaker. So we are choosing the 2 segments from 2 different files that have been pronounced by the same speaker. And to finish, the last one, the cross file with the same speaker and the same book. So that's the same as the previous one, except that the sentences that have been extracted are from the same book. So the objective of that was to evaluate the impact of these segment level strategies, but also to analyze their performance within tire operate at layer 2 and 3. So here are the results. So at the bottom left of the slide, you can see that for the second layer, when we are choosing our 2 segments randomly, we excel in all metrics. But for the third layer, we seem to have a bit better result when we are choosing the segment with the cross-file strategies, so with the same speaker and the same book. So it seems to suggest that selection strategies influence information encoded in different layers. So now that we know that there is important information at the layer 2 and 3 with different section level strategies that can be used, we have proposed a new kind of architecture. So we have called it the dual tire architecture, because we have added another tire module on the original T-codec architecture. So the aim of that was to capture as much information as possible. So basically what we did is that on the original recipe of the T-codec, the extraction are made from the second layer of the encoder, and the result is injected into the second layer of the decoder. And we have did another tire module that will extract its representation from the third layer of the encoder and inject the result into after the first layer of the decoder. So here are the results. So we have trained 2 systems. So the first one is our baseline. So the layer 2 and for the layer 2 and the third layer, we have used the random segmentation level strategies. And for the second system, the only thing that we've changed is that for the layer 3, we have applied the cross-file segment strategies. So as you can see on the 2 table, the performance of dual tire doesn't consistently outperform on all metrics, but it seems we noticed an increasing of the value in the Viscol, STY, MCD, and similarity speaker metrics. And the particularity of that is that it also performs on in-domain, but also on out-of-domain dataset as well. So on the right of the slide, that is the result that we are obtaining when we are testing the model on other languages than English, even if the model has been learned essentially only on English. So to conclude, we have seen that the tire consistently improve speech reconstruction over no tire. We have made a layer-wise analysis. So it seems that the second layer spotlights speech quality and session or channel effects, while the third layer spotlights perceptual similarity and speaker-related features. And we also did the segment level. We have noticed that the segment level strategies are layer-dependent, because the random seems to perform the best at layer 2, while the crossfile with the same speaker and the same books perform the best at layer 3. And to finish, we have proposed a new architecture of the decodec that doesn't outperform in all metrics, but seems to excel in Viscol, STY, and MCD in domain dataset and out of domain dataset as well. So now I'm going to let the speech to Liliane.
Do you guys have some comparison with the existing open weight model like a DAC or encodec or the MIMI or whatever?
Sorry?
So we don't compare the other model because the idea was to have a codec in string task. So it's why we don't compare with, for example, wave tokenizer. That is not possible to have this kind of model in streaming mode.
Okay.
So we just focus on T-codec.
Okay, okay, yeah, thank you.
Okay, thanks.
So I continue by talking about pseudonymization. The idea is to develop a system where first step, you are able to identify, the system is able to identify in the signal words that are considered to be sensitive words, words that identify a person, name, address, etc. And then the system should provide some replacement, suggestions for replacement of the same nature of the words that have been identified as sensitive words in the signal. Another step of the system should be the synthesis of these words that have been suggested as replacement words. And then we should be able to come back to the signal with the words that have been synthesized to replace the sensitive words that we get in the beginning. And then to tackle the two main parts of this system, for the part of identifying sensitive words, we have used named entity recognition with a pre-trained camembert that, and a model that has a classification header for named entity recognition. We trained that with a data set in French, that is Square data set, and we've got some good results, identified named entities, person, organization, for example. For the part concerning synthesis, we are working in the team with a neurocodec approach. And then the first one that we have tested is with the wave tokenizer. So you would like to make a TTS codec, and then we work it with Tacotron 2 as a TTS, and combined with the neurocodec wave tokenizer. That is a tokenizer that produces good quality audio, that it's small, that produces 40 or 75 codes per second. So what we did to combine these two bits to make the TTS codec was a little modification, the Tacotron 2. Originally it produces embeddings with the dimension of 80. We have changed that to a dimension of 512 to be consistent with the dimension the wave tokenizer works with. So we worked with the decoder part of the wave tokenizer, and then we passed the output of the Tacotron 2 that have been modified to this decoder of wave tokenizer that works for us as a vocoder. We have trained that with the Linda Johnson speech dataset in English, and it produces sentences that are intelligible, but they have a robotic quality. Another experiment that we did with wave tokenizer was to check its ability to incorporate an external word into a sentence that we have as a base, to see if it could integrate this external word in a smooth way. So to check that ability that we would like to see if it could do, we made an experiment with 3 conditions, like with 3 types of modified sentences. The first condition was a modification, was a simple cut and paste to put the external word instead of one of the words of the original sentence. Modification in the signal, that's the first condition. The second condition, type of modification, was taking the type of sentence that I just mentioned, type of sentence 1, and we encoded it, then decoded it with wave tokenizer. And a third type of modification was taking the sentence of base that was not modified at all and encode it to have a string of codes, take the sentence of type 2 to get from the codes the word that is the replacement, and make the replacement in the codes level, and then decode that. So we had the sentence type 1 is just a cut and paste, and the other two conditions involve the use of wave tokenizer. And then we would like to check if how smooth wave tokenizer could do that integration compared to the simple cut and paste. As a subjective evaluation, we hear that indeed the word insertion with wave tokenizer is smoother than the condition with a simple cut and paste. And we used objective measures as well to check that with measures of naturalness, intelligibility, and signal quality that my colleagues that are responsible for metrics in the group, they developed in a package. So they have a slide window form of doing that for the whole sentence. And then we got measures along the sentences. And then we were interested in checking the part that consists of the insertion of the external word and the neighboring part of it, the context. So we checked that. I'll show first just an example of one sentence, just for illustrative purposes. So with their package, they can provide us with some graphs and with the measures as well. So they are measures of naturalness, of intelligibility, and also measures of signal quality. And then there I have the three plots that represents the three types of modifications. The first one on the left is the simple cut and paste, and the other two are the sentences that involve wave tokenizer in the process. And then we can see for the cut and paste that measures of naturalness will show that the cut and paste is worse in naturalness than the other two conditions. For intelligibility, it is worse as well, and for signal quality also. And then we made a group analysis to be able to tell if it's a significant difference or not. And then we performed repeated measures 1A ANOVA or Friedman according to assumptions of normality of the data and so on. And we used in our factor condition the three levels of type of sentence modification, and we checked the measurements of naturalness, intelligibility, signal quality in that region of the insertion of the word. And then indeed the objective measures show the same pattern as I had explained for that one single example. The naturalness is significantly less in the cut and paste type of modification than for the other two conditions. Same for intelligibility and same for signal quality for some of the measures that we had in that series of measurements that we used. And for the next steps, we should work with T-codec, as my colleagues were just saying, and then repeat these experiments to test the capability of T-codec of working with the insertion of an external word, how good, how smoothly it could do that. So I should repeat that experiment and use also the TTS codec to do the replacement of the sensitive words that we are interested in working with. For the named entity recognition, we should still define our own set of sensitive words. And we still need to choose an anonymizer to provide us with the suggestions for the sensitive words that we have in the signal. And now I invite Yannick to...
Thank you, Lilian. Is there any question for Lilian about pseudonymization? Yeah.
Thank you. Very naive question. Maybe I didn't really understand why you do the pseudonymization in the speech and not just on the text at the beginning. I think you mentioned it as a next step, right? To just operate on the text and then you do the synthesis. Or maybe something I didn't understand.
We use a cascade approach, so we take the signal, we need to do ASR, and then with the text we will identify the words that are sensitive, and then we will use TTS to come from the text to synthesize, and then we should come back to the signal.
Okay, so you see pseudonymization as a post-processing after you have like one signal, and not you see the pseudonymization as a post-processing and not as during the first TTS part, right?
Pseudonymization we do in the text that we will obtain from the signal. We should replace there, and we get some alignment to be able to come back to the signal and make the replacement with the synthesized words.
Okay. Okay, thank you.
To complete Lilian's answer, what I can say is what we want to do in pseudonymization, we want to work on existing audio recordings. We want to change only the part that is we want to protect. The other part of the signal we would like to let them intact. This is why we start from speech. Exactly. I understood. So now it is the conclusion of this presentation, so thank you for your attention, but it's not finished, there is 2 or 3 slides. To conclude, we have very, we've worked a lot during these 6 weeks intensively, but we started working 6 months before, on January, I think, we started this work. One people is not present today, it's Fethi Bougares, who led the team with me, but he also has to come back home during the workshop. But he made a very great job during the workshop, also the 6 months before, and the team, of course. And so what we have today at the end of this workshop is that we have concrete outcomes like this different data we collected and we shared, we released to the community. So there are different languages: Tunisian, Sarawak, Malay, Cuban Spanish, Bengali, Central Kurdish, and Kabyle. They are available on the Gigging Face, the data. I think some of them have most annotation. I don't remember. Yes. Yeah. So there is also very important metadata made by human. We do have also this implementation tool that is now available in the GitLab of the LUM, the Brno University Computer Science Laboratory, and also this proposition from Natasha's team on this new quality predictor. By exploiting the data we collected, we also generated some voice, some models, so they are also available, or they will be available very soon on the Gigging Face for the languages I mentioned before. Sorry, I'm lost. Okay. And there is also some solid, very strong foundations for future work, because the workshop is finished, but the work continues. So there is this implementation of the Thai codec that will be very soon available on SpeechBrain. There is also this work made on the analysis of speech representation, the work made on the prosody control that will still continue. There is also this work made by Iman about benchmarking different TTS for low-resource languages. So we have to extend this to other languages. And also this preliminary result on speech pseudonymization. And so at the end, we are here. I think we will continue working on that. So the end of the workshop is not the end of this collaboration. So we will continue working on this very global collaboration. So we were 22 members from different institutions from all over the world. So thanks again to the organizers, to GSU, to Brno University for this very wonderful event. It was very great pleasure to participate to that. And thanks a lot for next year, because for different reasons, they also invited some people in my team. And I would like to get your attention just for the final slide, because there is some thanks.
Terima kasih kita ulangi. Yaitu usaha. Gracias.
I think it's thank you in the different languages we work on during the project. Thanks a lot. Now it's question time. I think you could come, because I won't be able to answer all the questions.
Thank you. I have a question. Maybe I should have asked it earlier. It's more connected to the first part of the talk when it was about that we don't actually have a way how to evaluate the TTS. So in my view, there would be two scenarios for the TTS. One is that we really want to see it as a distribution of speech, which has all the problems that we have. We have different background noise. We even have errors. I want to say some word, but I say it differently. I don't know, maybe there's some emotion disturbance, accents, and things like that. But it is the part of the distribution. So in general, if we would have this correct generative model to do that, we could just evaluate the likelihood of some spoken sentences and everything like that. And that would be a direct way to actually have a best way how to evaluate the things. But of course, with today TTS, maybe that's not the thing that you would eventually want to do. Because maybe if you want to create a product, you don't want to generate from this distribution in general, right? Maybe you want to just, this would be some marginal distribution of the speech. Maybe you want to generate it conditional on some maybe high score that the human would give it, right? So there would be different ways how you would use the TTS. But maybe if you think of it, I want to use the TTS to actually generate something that would be used maybe for ASR, then I don't necessarily want to have just the clean speech, because this is not my objective. And I would see that maybe during the whole presentations, you made some steps towards like one of these scenarios that maybe you would like it to use. And I feel like that's not like clearly distinguished, that there are these two ways and what would be the goal. And I think that maybe it would be good to discuss that or determine that, because this is something important, I think.
Thank you so much. First of all, we insisted on the part that we need to evaluate the TTS in application, and in the next part, when Arilas mentioned the perceptual test, we try to use to define an application case, use case for the TTS to be evaluated. And I wanted to add one other point here, the difference between speech synthesis and TTS. When you want to synthesize a speech or synthesize a voice, you can synthesize a breathing, you can synthesize the sound that come out of your mouth. A human can generate this sound. But when we are talking about text-to-speech, we should respect the input text. And if you have a repetition in your synthetic signal, it's something that you don't want to have. Otherwise, you are not talking about a speech to text, you are talking about a speech synthesis. No, you are not talking about text to speech, you are talking about a speech synthesis. It's a two different model that we can discuss, first of all. And second, I completely agree with you that the evaluation should respect the need that is behind the speech synthesis. And for that, we try to address the application of TTS for speech synthesis, for speech-to-text translation. And in that case, I completely agree that sometimes a clean speech is not necessarily a good synthetic data for a training set, because in the literature we can find lots of studies that shows that data augmentation by adding noise can benefit to the training, the robustness of the model. And here we have the same scenario. If our TTS system has a very clean and monotonous voice, maybe it's not useful as much as data augmentation. And for that reason, we discussed a little bit the augmentation of the data by adding the speaker diversity and prosody.
Okay, thank you.
Just one additional information that you are right. Thank you very much for your question. There is also, we have experience that if we simulate realistic, for example, if you have like application, for example, if you have speech synthesis, text-to-speech synthesis in the airports that I need is different, yeah. And the thing that you have the evaluation, if you evaluate the speech in like the reverberation in these cases, you have like maybe your TTS is trained on just to synthesize intelligibility as it's not anymore synthesis. Our experience for that even like the way that people are perceiving in like when you have special informations, I think that people from Emma and play your part succeed to have some novelty on this. There are the people, even the people like listener gives different rate for different conditions. Yeah. And if we speak about low resource languages, as I mentioned, it's different. The expectation of the listener is different, and the evaluation should be different. And the problem also we have faced in TTS is that the expectation of the listener change across the times. The listener, for example, if you take, I think that Sam has experience on this, if in 2000, if you take database that are released on 2008, I think, yeah, from Blizzard Challenge, it's the listener has rate something, and you gave some rate, and you go like to the data set that they released on 2013, you will see that are different to expectation from the listeners, and the evaluation drop out. We cannot handle this. Yeah, you're right. There is a lot of sounds. As Sam mentioned, this is a very big issue, and the community of speech synthesis, most of the paper that came in on the community is about the evaluations, not about the architectures, but how to evaluate, because we can go on with architectures, but we don't have what we evaluate at the last time. Yeah, thank you. So you're saying that to have stable evaluation, we should get yeah, we can have this.
Thank you for the great presentation. I kind of enjoyed the entire part. I'm particularly kind of impressed about the kind of established protocol from the data collection, the evaluation, fine-tuning to kind of apply to various language, which I kind of think very kind of valuable. And then my kind of a question is that this kind of methodology can be scaled to up to the thousands of languages, or that it can be somehow goes to around 100 and may need some breakthrough. Anyway, I just want to kind of have your sense of how much kind of we can scale the languages. That is my kind of question. Yeah.
Yeah. I think there is already efforts on the community on this case. Mm-hmm. If you see, if you have there is what they call it massive corpora, massive language data sets that is already there with, I think that they assume there are 7,000 languages, mm-hmm. Yeah? And the thing that it's the next step for us is that we take this corpora and have scaling the thing. Mm-hmm. You're right that for us, the experience that we had is that for now you can say that it's maybe it's overfitting the data sets that we have. Mm-hmm. But one thing that I would like to mention, our experiments cover different founded data, like different from common voice and different like noisy informations and so on. But you're right. Maybe it's the next is we have to prove that it's like this pipeline is applying for all languages or different languages at least.
Yeah. Sounds good. Thank you.
Thank you.
Just one comment. We had almost same question at the beginning of the workshop. I don't remember by who said the question was who will buy such a result, such a product finally if you want to, I don't know, to work on the speech synthesis on the Cuban accent. And I was surprised when I see that in less than 24 hours, we had 80 listeners voluntarily respond to our call for the evaluation. And I think during my thesis and afterward, I tried to launch an evaluation, and I never catch this amount of the listener really volunteered for the evaluation for 1 week or even 1 month. So I think the community that is behind this kind of low resource language are ready to embrace such a tool and technology.
There is a bias when you speak about low resource languages. Most of the time, this motivation behind community is heavy for now. Like the expectation they would like to have normal, digital life, so they are motivated. That's why we have this.
Yeah, well, one additional comment. This is related a bit. So I've done machine translation in the past. I'm still a bit working on it. And we know that languages, they can interfere, they can transfer, so you can get from it. So I was wondering, for having TTS4ALL, would this kind of strategy also apply? Do you have an idea whether data set from different languages could really help together, and what language goes well together, and what language are should not be mixed, and so on? So is it something that you are willing to look at, and do you have thoughts about that?
Yeah, in fact, we had experience on those sense. There is 2 things that we have in mind: the languages approximations, but also speaker approximations. In the speech, if you speak about speech-to-speech translations from low resource languages to high resource languages, for language approximation you can catch up. I think there are people from prosody control can have look on this, that I more rely on the prosodic approximation rather than just signal approximation. Like prosody can be helpful for handling approximation between languages. One thing, and there is also this phonetic coverage between languages. We know that our phonetic at low levels, we have this approximation between, there is some languages that cover a lot of phonemes and others not more. For example, if you compare between my mother tongue and French has more 16 vowels and my mother tongue has only 3 or 4 things. I think there are language approximations, it's there, but there is 2 kind of things that we have to be careful. There is language closeness and low language robustness. Means if you are, for example, we show that for example for Spanish, you have approximation with Spanish, Cuban Spanish. This is what I call closeness. You have proximity, and you have pre-trained models, and you see that you are fine-tuning and transfer learning is going you can be sure that it goes to the Cuban Spanish. Okay. And we show that also there is one thing that about language robustness. It means that if you train your model on a huge data set in English with a lot of variations, and with different accents, you can have also good models that can handle other languages. Like my mother tongue there is nothing linked with English, for example, or others. But since that during the training from scratch, the model's seen a lot of variations and a lot of things. This is also depend on the models. Yeah, this is not only. But this is in the case of the robustness. The language, the model is catching a lot of context and can be generalized. I don't know if I answer your question.
Yeah.
I have a question maybe for the prosody people. I was wondering, like, for the representation of the prosody for generation, like in some of the speech generation softwares, like you can, for example, turn a dial to turn up the speed of somebody speaking or whatever, and that's like a human interpretable representation. And it's not as simple as like just speeding up the playback of the audio, because like your tongue can only move so fast and whatnot, so it changes the way you speak or pronounce things when you're speeding up. I'm wondering, does the prosody encoder, can you actually pull out maybe human, like interpretable parts of it? I don't know. Let me hand the microphone to you.
No. Suggest they come here because there are some YouTube capture, and so the people has to be here to answer. Sorry. Who will answer? Martin? Santi? I have a microphone.
You're going to hate me, but can you repeat the question?
No, it's okay. So for the like prosody encoder, can you like pull out sort of human interpretable like maybe numbers from the encodings, like in some of the other speech generators, like from 11 Labs or whatever, you can turn a dial and it turns up the tempo of the person's speech. So like it doesn't it's not as simple as just speeding up the audio. It's like it's actually changing how quick they say the vowels and consonants, and it changes.
Yeah. Sure, we think about that. We do some experiments. I think the main problem now, in order to do that, is that you need to define what in the literature is called intonation unit. So you need to define, this is my this segment is the unit that I want to analyze to then be able to do this clusterization. There are systems that automatically can label this kind of segment, but not for other languages. There are systems for English, and I think there is one for Mandarin, because it's a tonal language, and so it has other other kind of importance. But we were more interested in a representation that could be language agnostic, so we don't have for the other language easy way to do the segmentation to then see if we can work with clusters. So I think that is an interesting topic of research, but we are not too much into it for this particular work, at least.
Finn's question actually makes me think of a suggestion, which is, there are these labels that are used to mark like pitch contours, Toby. Like, high, low, whatever it is, that Toby-like system, Toby. Right? And then there is also this notion of like, is there where in the sentence is the prosodically most stressed syllable, or like, a couple of things. So what I was wondering is whether you could probe your embeddings by building a classifier to say, take an intonational phrase and say, can you figure out the label on it? Or give it a phrase and say, is the pitch accent in the first or the second half? Or you could design some probing tasks and see how well that representation can answer it.
Our idea is to add more tasks similar to the emotion classification that we do, because we know the prosody is important for that.
Yeah.
We plan to add some other ways to assess that the embedding has information for the different component of the prosody, because it's not only emotion, you have accent, style, dialect, maybe. Yeah. And yes, this,
like, in some languages, there's a simple difference between question and statement, and see if this can do a binary class. The thing is to go after things that are explicitly prosodic, rather than something like emotion or whatever, like, you know, which can be much more diffuse. It doesn't.
It's not easy to isolate for a problem to be only processed.
I think Lara has some opinion.
We start working on a dialect classifier because as I mentioned, in Spanish, there's a lot of difference with the prosody, so if this classifier works well, that means that we are doing a great job with the prosodic encoder.
Okay,
so, yeah, that we will have a case of use that only focus on prosody, so yeah. But the problem is, again, it's a low resources scenario, so the data set maybe not very well recorded, and we don't want to classify, I don't know, other information like the microphone and so on.
Yeah,
so
no,
because of that, we don't present.
But you could train the prosody encoder with all sorts of data. It's like how you do X vectors, right? You train it on some other data set, and then you apply it to the data you care about. So you could train this thing on all the speech in the world. You don't have to be limited to, right? Yeah. And I was also thinking, even simple tasks, like, you know, there are some pairs of languages which are otherwise similar, but their stress patterns are different. So I wonder if you could do some simple tasks like that, you know, say classify between this and that language, but give it only the prosody encoding. And that way you can see if it really encodes, like, you know, and you know from linguistic knowledge that the key difference between these languages are the stress patterns. Something, or maybe tonal versus non-tonal language. See if it codes information to distinguish between the two. It's not a task it was trained for, but if it can do it, you know the embedding has that information. So, good thoughts, Finn.
Thank you.
Are there any more questions? So it's time for lunch. It's okay? It's okay, Chanchiv?
Yes, it's okay. So we are on time, which is beautiful. Yeah. So let's try to reconvene at the hour that we have set, and that was, I have no idea, 1:30. Okay, thank you. So 1:30 back.
And my team, could you come here, please? We would like to take a picture. Thanks a lot.
Sorry, I'm Sarah. I'd just like to let you know that Mesam and Aguilas is very, very humble with their evaluation package. Actually, they are involved in the, I think as mentioned, they are involved in the Blizzard Challenge, right? And in this workshop, we just found out that their solution was rank 1. So they're just being humble and they don't want to say anything about it, but I think this is really good. And I hope for the best for the interspeech when they talk about the Blizzard Challenge. Thank you.